a number of programs, including a lot of astronomy, also geared towards electro-optics. And then after that, he joined a small company. He wanted to join a small company, SVS, out of Albuquerque. And he worked out of his home in the Front Range foothills, beautiful place he had in outside of Bend.
Not Bend, Boulder.
Yeah. Okay. Well, it's outside. It's in that area for the people here. And I remember we got like 8 inches of snow one Labor Day there. What altitude was your house? It was like 90?
8950.
Yeah, he lived at 8950 feet. And SVS was bought by Boeing. So Ed worked for Boeing for quite a while and was a Boeing fellow and retired. And he now tutors, he teaches, he gives lectures on cruises and writes books with me. Go ahead, Ed.
Okay, so welcome.
Everybody else but Ed to mute.
Yeah, welcome everybody. I'm going to share my screen and immediately go into presentation mode. So you should be seeing something that looks like a presentation strategy. And tonight I'm going to talk about the early universe. And by that, I will describe what we mean by early, but we're talking about, emphasis on the first 10 minutes of the universe, and then some implications we get from signals we can see from somewhat later, about 380,000 years after the universe started. So here we go. So let's talk about what we're going to cover. I just said this. We're going to talk about a timeline that goes out to 400,000. Well, let's forget that. Out to 380,000 years, because that'll be important a part of our story. And we're going to talk about formation of the constituents of the early universe. And the striking thing about this is you'd think that we wouldn't know very much about a time so long ago, but the fact is we have an understanding at the intersection of completely independent scientific endeavors that are self-consistent. And those endeavors include subatomic physics as studied at the big accelerators, theoretical models about how those subatomic particles form into the constituents of matter, observations based on astronomy using completely different strategies. So we're very confident we understand what happened in the early universe. And it's a great human interest story too, as you will see. And I will talk some about what we're doing these days to continue to refine our understanding. And I've already said this a few times, the significance of 380,000 years. So the key things we'll talk about: Big Bang nucleosynthesis, that is formation of atoms, the lightest atoms in our universe in the very early minutes of the formation of the cosmos. And we will talk about the cosmic microwave background, which is something we see today, and that's associated with this 380,000 year thing. Okay, so here's a cartoon of the universe and its history. Over on the left in this darkest area is just an unknown territory. And early on, something happened that caused this, what we now call inflation. And we'll get into that. I don't want to talk about it quite yet. Inflation meant there was explosive growth in the size of the universe in the very earliest times. And by early times, I'm talking about the tiniest fractions of a second, 10 to the minus 25th seconds or something like that. After inflation, atoms formed. And we'll talk about what that means. But for a long time, those atoms were kind of isolated. The universe was dark. There were no stars. until about 400 million years after the birth of the universe. Up until that time, the universe, except for the bang itself, the universe was dark. And that is kind of extraordinary, because the early universe was, I mean, this tiny fraction of a second after the universe started, incredibly bright. Nothing could survive. In fact, atoms didn't exist because the radiation intensity was so large that any pair of electron, let's say an electron and a proton, decided they'd like to get married, at the ceremony where they say, does anyone speak now or forever hold your peace? A high energy X-ray would arrive and say, no, you're not getting married. And so it was just a cloud of parts of atoms and parts of atoms. Eventually, it was cool enough for atoms to form, but they're just isolated. We have this period called the Dark Ages, and the first stars, which we can see the first galaxies now, finally. No stars until about 400 million years into the process. So I've said all these things. This happens. So if you're a reader, if you would prefer to read, these are the words I just described. And galaxies forming around 1 billion years after the birth of the universe. And I put a little asterisk because these numbers bounce around a bit. In fact, there's controversy now about some of the results from recent measurements that are right in the forefront of modern research on the early universe. So when we say early, as I've said a few times, up to 380,000 years, that's what is really our interest tonight. We're not going to talk about the Dark Ages where there were no stars. But we, as I've already said, we know a great deal about the time near time zero. And as I want to emphasize throughout this talk, we have many views of that using different scientific techniques that are quite independent. And so from a time of about 1/1000th of a second forward, we have insight into what was going on. And the reason we can make pretty concrete statements is that we can see the amount of individual periodic table elements, hydrogen, helium, lithium, beryllium, and so forth. And we will get into that as we go through this talk. There's a few notes here. If you want to grab the charts from me or Bruce, there's some links here that talk about, that provide you with more details. Okay, so here's how we gather our information. For a long time, we were relying on ground-based telescopes up until the launch of Hubble, and we could see back. Notice how this graph works. The arrow shows you, if you go down here, you could see back to the time before, the time after the Big Bang. So from the ground, we can see times, or looking at galaxies that are, say, 6 billion years old, because the birth of the universe is off to the right on this chart. In 1990, Hubble was launched and there were troubles, you may remember. It finally became a productive scientific instrument by 1993. And one of the interesting experiments that was done early in Hubble's lifetime was to do something called the Hubble Deep Field, which is a long exposure of a spot on the sky that prior to this date looked completely black. But the management of the Hubble telescope said, let's point the telescope whenever we have spare time. Let's point it at the darkest spot on the sky and just take a long exposure. And they found a dense array of primitive galaxies. And those galaxies were about 1.5 billion years old. Now remember, I've already said that the first galaxies started at 1 billion years after the bang. So these are galaxies formed very close to the first galaxies in the universe. Later on, 10 years later, Hubble Ultra Deep Field was performed, again, integrating long exposures over weeks, and produced these beautiful pictures of ancient galaxies. And the the Ultra Deep Field reaches back to a time right when galaxies were forming, around 800 million years. Now notice I said earlier that galaxies formed at a billion years, and this drawing shows 800 million. This is what I mean about there's some fuzziness about how people are interpreting the data, but the work continues. Another interval occurred where by 2010, they were doing deep fields using infrared telescopes or infrared instruments on Hubble. It has limited capability in the infrared, but we actually have imagery back to 480 million years after the bang. So this is right after stars formed. And upcoming, we hope, in 2022, I think, the James Webb Space Telescope will launch. And it is designed to look even deeper. It is a truly infrared telescope. It looks at the oldest, most distant galaxies and stars. And because of it, it's working in the infrared region. It will be able to see deep into the cloudiness of galaxies. You know, galaxies have individual stars, but a large part of the observation we make of galaxies involves dealing with the dust and debris that's floating around in those galaxies. And it's easier to see through that dust by using infrared science. And so James Webb, which is focused on that, is expected to see way back. And now, some of you have heard that the universe is expanding. So let's take a look at what that means. So here we are, present day, once again. Now this drawing is a little different than the one, well, I guess it's the same, the one I just showed you. So this is years since today. So we reach back to the Big Bang. It's about 13.8. Some data shows 13.5 billion years since this event that started our universe. And this is pretty much the same kind of data I just showed you. Shows you the oldest galaxies that we've observed. And here's something important to understand. If you look here, actually up here, if you look at this scale, it has a way to designate how old the material that we're looking at is. And this is the same drawing, drawn slightly different. What this illustrates is that when you get to a Z factor, that's what this scale up here shows. So when you're at Z13, kind of like right there, the objects that you're looking at are receding from us very close to the speed of light. Objects that were formed at the Big Bang are at least going the speed of light and maybe going faster. We cannot observe them. And that's, by the way, before there's a bunch of questions about this, objects can recede from us faster than the speed of light because the universe is expanding and the oldest parts of the universe are leaving us at faster than the speed of light. And that's not a violation of relativity because the objects that we observe at these great distances are not moving through the local space that they're embedded in. It's the space between us and them that's expanding. So that locally, if you could go out there and look at these galaxies, they're moving, but they're being carried away from us because of the expansion of the universe. And the oldest galaxies we've seen are receding at very close to the speed of light. So Big Bang nucleosynthesis, which is exactly what it means. Nucleosynthesis, the synthesis of nuclear particles, which lead us to atoms. And there's an interesting history here. Little was known, well, first of all, the history really starts in the late 1930s, when when there was the first serious and successful application of modern physics, and namely quantum mechanics, to understanding how stars produce light. And Hans Bethe, who was then a young scientist based at Cornell University, produced a theory that explained, for example, how our sun produces light and produces elements that were not available in the early universe. We'll get into this in a little more in a few minutes. So Bethe, by the 1938 or so, began to understand the nuclear physics that goes on in a fusion process where hydrogen is forged into helium and other materials. That's also right on the doorstep of World War II and the production of the atomic bomb. And in the late 40s, so after the war, George Gamow, a kind of impish character from Russia, was in the United States, had settled at George Washington or Georgetown University in DC, and was a professor. And he had this idea that all the elements that exist in the universe were produced in an early explosion where there was immensely hot, dense gas that forged those elements. And he turned to his students to compute how much of each element in the periodic table should exist. And observational astronomers measure this sort of stuff all the time. They look at galaxies, they look at the spectra of the galaxies, and they can figure out what are the components of those galaxies or clusters of galaxies. And observational astronomy was making big strides in the late 40s. They had big telescopes like Palomar and more inventions coming to do a good census of what is the composition of the universe in terms of elements in the periodic table. So he turned to his students and he said, compute from what we know about nuclear physics, some of which came from the work prior to World War II, and some came from declassified information about the creation of bombs. And so he had challenged his students to figure out if the entire periodic table was formed in a hot ball of gas that started the universe. And they found out that he was wrong. And there's a specific reason why, and that involves neutrons. To build a complex atom, let's say if you start with an electron and you want to build the simplest atom, hydrogen, you need a proton. After that, if you want to build more complicated atoms, you need to add neutrons and protons of the right amount so that you have a stable nucleus, and electrons will be interested in gathering around that nucleus, and you will have an atom, say, of carbon or oxygen or something else. Here's the problem. Neutrons, even in the late 40s, it was understood that neutrons decay in minutes. And so in the early universe, if neutrons were present in abundance, within a few minutes, the volume or the density of neutrons would have dropped dramatically for two reasons. One, neutrons are not stable. They decay into protons, electrons, and a weird particle called an anti-electron neutrino. So neutrons are not stable. Moreover, the universe was expanding dramatically in the early days of in the early seconds of the universe. So a cloud of neutrons that you might have gathered together in an attempt to build, say, a nitrogen atom, because the universe was expanding, all those neutrons were flooding away from each other. So that it became more and more rare for groups of neutrons to be available to populate a nucleus and build heavier atoms. So we had two factors. I'll show you what we understand about that in a second. So there just wasn't enough time to build up the heavier elements before all the neutrons had dispersed, and there just weren't any free neutrons floating around. So where did the stuff we're made of come from? Well, we have a lot of hydrogen in us, and we have a lot of nitrogen and so forth. But if you want to know where iron came from and aluminum and so forth, those elements they found were made in stars once stars were formed. So the early universe, I've already told you, it took 400 million years before stars formed. And in the crucible, in the interior of those stars where fusion process was going on, that's where the heavier elements were created. And as those stars aged and died or blew up, those elements were thrown out into the universe, swirled around for billions of years, and gathered together later in other stars, and the process continues today. So as Carl Sagan very famously said in his Cosmos series, we are all made of star stuff. So we think we understand this. Now, a byproduct, a very important byproduct of the work done by Gamoff's students was that they said, well, we actually, from looking at the nuclear physics of these processes, we can say that we should be able to detect an afterglow of that first explosion that was the formation of the universe. And we should see it on the sky if we looked for light that's not light visible to humans. It's light that has been stretched out by the expansion of the universe, and we should look in the range of wavelengths, in what are called microwave wavelengths, that are at about 5 degrees Kelvin above absolute zero. That was an important thing. Now remember, we're at like 1952 or something like that. We'll talk about that more in a second. So you should understand that when you want to build heavier and heavier atoms, you have hydrogen here. And this, by the way, is a highly logarithmic scale showing the abundance in our current universe. Hydrogen is the dominant element in the universe. It's everywhere in high concentrations. It's about 70% of all the stuff that we're made of, or that's in the universe. Helium comes in at about 25%. And I'll show you why in a minute. So now we're adding neutrons and protons to build more complicated atoms. This is going on. Once you get out to about this point, once you get past boron, all this other stuff was made in stars. But hydrogen, helium, lithium, beryllium were made in the Big Bang. And it has this funny kind of sawtooth behavior because as you add neutrons and protons, the abundances change because of the creation of radioactive versions of these elements and so forth. So, but this is very well understood, and astronomers have measured this concentration of elements in the universe. And here's George Gamoff. He was famous for little puzzles and poems and songs and stuff. So he has this Twinkle Twinkle Quasi-Star, which we're not going to talk about tonight. These are non-star, these are stars that don't produce light using normal processes. And when George Gamoff wrote this, nobody knew what quasi-stars were, quasi-stellar objects were. And he says, these are the biggest puzzle from afar, how unlike the other ones, brighter than a billion suns, twinkle, twinkle, quasi-star, how I wonder what you are. We now know what they are. They are the emissions from the debris disks that circle supermassive black holes, which were not even on the list of candidates when George Gamoff was active. Incidentally, Gamoff became a professor at the University of Colorado near where I live, and was notorious there as well. Now here's where he's an example of his notoriety. This page emphasizes this character, Ralph Alpher. Alpher was one of Gamoff's students. And Alpher made tremendous contributions in the late 40s, early 50s, doing his PhD in understanding the nuclear physics associated with the formation of elements in the early universe. His doctoral thesis paper was published in 1948 with Gamoff, his advisor, and Hans Bethe, who I've already mentioned. Hans Bethe was the one who figured out what goes on in the sun to produce the light we see and the elements we see. Bethe, very Nobel Prize winner for his work on the processes in the sun. The story is that he was at a conference in 1938 and somebody presented a very convincing description of the process of formation of elements and light deep in the sun. And Bethe watched with interest, and he thought about what he had just seen and decided there was something missing. And he went back to his room and he spent the evening and the rest of the night working on a new theory. And by noon the next day, he presented a paper that explained everything. And subsequently, it remained a famous and highly productive physicist until his death. So back to Alpher. So Gamoff was supervising Alpher's work, and he insisted on including Hans Bethe as another author on this doctoral thesis paper. So that we would have three authors, Alpher, Bethe, and Gamoff. And Gamoff, I mentioned as an impish character, he thought it would be amusing to have three authors whose names sounded like the first three letters of the Greek alphabet, Alpha, Beta, and Gamma. So they published this paper, and it made tremendous impact on the way people thought about the field of cosmology, which at that time was essentially dormant. Nobody was working on it because we didn't have the big telescopes we have now. The theories were primitive. There were no computers. That was a big deal. So everything that was done, with mechanical computers or slide rules. It was really difficult to get results. So this paper was a landmark in the development of cosmology. And because Alpher was a student, Gamoff and Bethe got most of the credit for the work. The presumption was that Alpher was included only because of his name. So they could do this amusing coincidence of Alpher, Bethe, and Gamoff. But it turned out Alpher did most of the work. And in reality, he fixed technical problems, mathematical problems, and unfortunately became fairly bitter about this experience. He thought that he had contributed significantly to a breakthrough in understanding the history of the universe and should have been a candidate for a Nobel Prize. But there was a lot of prejudice about the inclusion of his name being a joke. Now, he and his colleague predicted this signal, the microwave signal I mentioned. So there's a second contribution they made. Alpher was awarded the National Medal of Science by President Obama just shortly before he died. His experience dealing with his professor and famous people raises ethical questions about how students interact when there's something significant going on. And there are many, many examples of this. And this is not the only case where students' contribution was overlooked. And a few years before Alpher died, my mother hosted him because my aunt married his brother-in-law. So here's a picture of Ralph Alpher at my mother's home, probably around 1975. But I know people who knew him well, and he was bitter about his experience, and rightly so. Now, here's a page from a the National Academy Transactions, that's what NAT means, from 1948. This is from Alpher and his colleague, another student, Herman, where they discuss some details about when the universe would first start forming atoms, and could we see an afterglow of the Big Bang. And right here in 1948, they predicted detecting that signal at 5 Kelvin. And actually, both of them, I believe, were working at, there's a research lab still in existence that's associated with Johns Hopkins University. Both of them were students and were working at the same time. And they mentioned here the computer they were using to do calculations of the formation of heavier atoms. And it was based on something some of you might have heard of, analog computers or operational amplifiers is another term for that. So here's the kind of, and now this is a modern depiction of what happened to the temperature. So here we have temperature right after the Big Bang. Notice we're starting at a very early time, 10 to the minus 45 seconds. So this is the instant of the Big Bang. And we're up in the vicinity of 10 to the 32nd degrees. Things were pretty warm. And as the time scale progresses, once again, highly nonlinear, this is advancing in gigantic steps. The temperature is dropping and dropping and dropping. And this is 1 second after the Big Bang right there. The temperature was still here at 10 to the 11th degrees. But that's just on the edge of beginning to have condensation of subatomic particle components forming into neutrons and protons and so forth. And as I explained, you need those before you can have a wedding where hydrogen is formed. And that happened here when the temperature in the universe was about 600 Kelvin. Okay. So here's the same drawing, but I'm going to expand it a little bit. This shows a little more detail, so that at 1 minute after the Big Bang, we have formation of the lightest elements: hydrogen, helium, lithium, beryllium, and a bit of boron. And then after, well, you see a marker here for years. This indicates that the amount of matter that has formed is more important than the amount of radiation in the universe, the radiation being forms of light. But remember, the universe is expanding, so the density of radiation is being diluted because the universe is getting bigger. And then there's some other events going on. There's a link here you might want to follow if you're interested in this, to Ned Wright's webpage on formation of or the processes that occurred in the early universe. Here's yet another drawing, but I want to show you this because it's very clear on where we are in terms of the temperature of the universe, which I appeared once, but let's look at it again. So here's temperature falling dramatically. And right now, if you go over here, you'll see we're actually, the prediction of Ralph Alpher and his colleagues of a 5-degree average temperature for the universe was very close to the value we have now, which is at 2.7 Kelvin. So they were very close to the right answer. Now there's a weird story here too. There was a group in the early 60s at Princeton University, a very tiny group dealing with cosmology and these issues. And they were speculating about these things that are shown on this graph. What was the temperature history of the universe and when did atoms form and so forth? And they would give each other presentations, not unlike the one we're doing right now. They just would talk about their progress at the university. Not far away, about 40 miles away, Bell Telephone Laboratories had a research facility that at the time was famous for its many, many inventions. And occasionally they would send a scientist over to Princeton to listen to a seminar. And one of those guys attended a seminar where the cosmology group at Princeton, led by Bob Dickey, talked about a chart like this one, which was much cruder at that time. And in it, in the seminar, there was discussion about, could there be a signal that could be detected? And the visitor from Bell said, well, we have a project to study the sky, to develop technology to convey communication via microwaves. And every time we point our antenna at the sky, we see a background glow, and we're trying to get rid of it because it interferes with our work. But maybe what we're seeing is what you are looking for. And this, one of the character who was there, I believe, was Penzias. And he and his colleague Wilson, 6 years later, won the Nobel Prize because they, in fact, had detected the glow of this faint background signal at 2.7 Kelvin. And that was the beginning of modern cosmology, where we finally had observational techniques to confirm what we were thinking about. So this is a little more detailed. So now let's talk about nucleosynthesis, the work that Ralph Alpher really started. And this statement kind of captures everything. The abundance that astronomers find of the lightest elements is predicted by the standard cosmological model. And this model stands atop the standard model of subatomic physics. I'll show you details. And the lightest elements were formed right after the Big Bang, within a few minutes after the bang. And that was Big Bang nucleosynthesis. And the heavier elements were produced in stars. So this is the most important drawing in this presentation. Let me explain what we're looking at. This is a logarithmic scale showing the abundance of various elements. They're listed here. We'll talk about that in a second, ranging from the number 1, which means 100%, and ranging way down to a very, very small number. And this is the time in the universe. So as we go from left to right, we have over here, we have a Big Bang, and in the Big Bang, the very earliest formation was of hydrogen, and D stands for deuterium. So after, and here's that mysterious neutron curve I mentioned. Here's the neutron density, which in the early universe was big. It was 3 or 4% of, if you took a cubic meter of the universe and analyze it, you'd find 3 or 5% of what's in that volume was neutrons available to help build heavier atoms. But notice it's drifting down and down and down. And we get to 100 seconds. That's when the effect of the instability of neutrons starts getting noticed. And keep in mind, the universe is expanding. There's a limited number of neutrons formed in the bang, and they're getting diluted as the universe gets bigger. So we have this dramatic drop off here. And the neutron density now, today, is, if you go out and grab a cubic meter of universe today, there's almost no free neutrons floating around. So this is what Alpher and Herman found, that because neutrons are depleted by 2 mechanisms, the formation of heavy elements was cut off. Now here's what's interesting. YP stands for, that's the density of helium. And it's, that arrowhead's pointing in the wrong place. It should be pointing right here. That's about 24% of the mass in the universe. So right now, you can really barely see it. That's hydrogen. Very close to, say, 75% of the universe. I apologize, that arrow is wrong. 24% here is helium. And then you have isotopes of various things. So deuterium is a heavy version of hydrogen. You have helium-3, you have beryllium, and you have lithium. And if you talk to the astronomers, they will tell you, hey, these numbers that we observe in galaxies are just about right. There's a little problem here with lithium, which I will describe. So this is a very important curve. And oh, these curves, these are not measurements because we just can't see in enough detail that early to do a census of the density. But the model that was first created by Alpher and Herman is now highly refined, and it predicts these values that we see here. So we're predicting a concentration of lithium-7 of around 3 × 10⁻11 in terms of mass in the universe. So the current models predict these values, and they're very close. Let me show you some examples. And here's the times. Neutrons. Okay, so this is an example of the process. A proton and a neutron form to produce this thing, which is the nucleus of a deuterium. And the deuterium, 2 of these can fuse to make hydrogen-3. And then hydrogen-3 can interact with yet another deuterium and you get helium-4. So there's these processes go on. They're very complicated. Here's one that shows helium being synthesized by hydrogen. So you take a group of 14 and this we understand because this experiment can be done and is done in universities everywhere all the time. And we see this happening in various kinds of experiments in an attempt to create a fusion process to make electric power for our consumption. If you take 14 protons and 2 neutrons, and they go through a complicated process, when you get done, you get 1 helium atom and 12 hydrogens. And if you do the arithmetic and calculate the masses involved, that tells us that the mass of hydrogen to helium should be 75%. And that's what we observe in the universe. Remember, I said most of the universe is hydrogen, there's some helium, about 25%, and then there's traces of other light elements. And the reason this works is the leftover hydrogens are, of course, lighter than the 1 helium that was produced. And if you count the number of protons here, which is the dominant mass, you find there are 16 and 12 are left as hydrogen and 1 is a helium. So you get 12 over 16, 75% of the universe should be hydrogen, and that's what's observed. Now here's an example of the equations. They're similar to what you might have seen in high school or college chemistry, that you have a proton and a neutron arrives and you get a deuterium nucleus. And we already described that produces a helium-3, and then you can have another deuterium hit it and you get helium-4. And if a proton arrives and hits the helium-4 just right, you can get lithium-7. If it hits it a different way, you get beryllium-7, and that changes into lithium-7, and it's just a crazy set of equations. And here are some samples. So in neutron, proton, electron, here's that strange particle I mentioned, a neutrino. And so these things are being created through different equations. Proton plus neutron, you get deuterium, we mentioned that. And here's the deuterium, which when hit with the right energy by a proton produces helium-3 and various other interactions. So here's helium-4 interacting with tritium, a heavy version of hydrogen. And those 2 guys, a tritium and a helium, can produce lithium. And by the way, it took until the 1960s to explain. There's one thing in here I don't want to go into. It's very technical. There was a so-called deuterium bottleneck where people could not understand how the processes got beyond that point. And it later turned out there's a very complicated nuclear chemistry equation like these that was used to explain how that bottleneck, how nature avoided that bottleneck. So this is supposed to be a guy being shocked by the complexity of this. And so this is what Ralph Alpher was solving. How do you calculate the production of elements when you have so many things going on at the same time? Now here's the lithium problem. And it introduces us to this very nice curve. So here's the abundance of light nuclei that we observe in the universe. Once again, a logarithmic scale. And on the horizontal scale, this is very important. This is the density of matter in the universe. That is, of all the energy types that can exist in the universe, light and infrared radiation and particles and other things that we will discuss, what fraction is the stuff we're made of? And here's the model for deuterium, helium, and lithium. And because the versions of hydrogen and deuterium, tritium, and helium are the most abundant, we have to get this curve right. And here, these bars, this orange bar is what we measure. Deuterium measured in the universe by looking at galaxies, and we get the predictor doesn't know what the density of matter in the universe is. The model has a single knob you can turn. So you turn that knob, how much matter is in the universe, until you get the right number for the amount of deuterium. And when you do that, you also get the right number for helium, and you almost get the right number for lithium. Here's what we measure for lithium, this horizontal bar, and here's what we predict. So there's an issue here with lithium, but all the other light elements work when we assume that the density of ordinary matter, that is the atoms from which we are made, if that represents 4% of the mass energy in the universe, the energy of all kinds, we get the right answer for the most abundant components.
And this is John. We got a little issue here. Bruce, a neutrino is not an electron. There was a question asked, what is a neutrino? And that's a very complicated question. It's a subatomic particle that probably has no mass. Can you comment just about 10 seconds on that?
Yeah, 10 seconds. So neutrino probably has a very, very low mass. We can detect these. They're produced in abundance by nuclear reactors and the sun. They are the topic of constant research. 3 Nobel Prizes have been produced explaining properties of neutrinos, but they are essentially massless particles, not exactly, but very close to massless, and there's 6 kinds of them. So that's all I want to say right now. Now, if we have time, I can talk a little bit more about neutrinos. So I want to go back to, oh, and they come in different flavors, and I might have used the term electron neutrino. There are different kinds of neutrinos. Like there are different kinds of football players. There's the Seattle guys and the Washington guys and the Tampa Bay guys. But they're all playing football. And all the neutrinos are neutrinos, but they're associated with different teams. Okay, so what this curve tells us is that we better explore for an independent way to determine how much of the universe, of all the types of energy in the universe, are related to the atoms from which we are made. That's really important. Now, here's another look at this. Here's helium. This is the abundance of helium in the universe. Remember I mentioned it's a kind of like 25%. Well, it's somewhere right in here. This box tells us what is measured. And this magenta curve is the model that depends on this density. That is, read this as matter density in the universe of atoms of our type, the stuff we're made of. There's another kind, which I'll mention in a second. So we have this box of measurements right around 25%, which is what the model predicts. And it matches the model right here if we have a matter density of around 5, you see this orange cross-hatching that goes over here, between 5 and 6.5%. That is, if 5 to 6.5% of the universe is of atoms like us, then the model predicts what we observe, because the observations are in the yellow box. Same thing here with deuterium. Now there's another cross-hatching here. See this cross the other way? And it says CMB. Keep that in mind. We'll talk about that. It also predicts the same kind of result. And I'll show you how that works. And it's a completely independent process to make that calculation. Here's Big Bang nucleosynthesis, the slashes that go that way, and the cosmic microwave background agrees and is in this range. And then we still have this problem with lithium, and people are working on the lithium problem because here's the prediction, and it doesn't match what we measure, which is in the yellow box for these matter densities. But we can explain, say, 99.99% of what we observe in the universe. And right there, we have agreement between two completely different measurement techniques, Big Bang nucleosynthesis and something called the cosmic microwave background. That's the glow that Alpher and Herman predicted in 1948. Let me show you about that. So here's a picture of the cosmic microwave background. This is, you have a special telescope that does not see stars or starlight or infrared light or anything. It sees microwaves, kind of like what's going on inside your microwave oven. And there's some variation. This is the entire sky, by the way. This is the North Pole and the South Pole. And this point here and this point here are the same point. So you essentially have drawn a projection of the interior of a sphere, and you've drawn it in 2 dimensions. There are versions of this that are used to try to depict the surface of Earth, which is a sphere. So we have these areas that are hotter. There's some red here and there. There's a hot spot there, and they're cold areas. The variation between the coldest and hottest is 1 part in 100,000. So the glow that we see on the sky from microwaves left over from the Big Bang is essentially uniform, except for this tiny variation. And this has been a subject of space-based missions for the last 35 years. 2 of them have led to Nobel Prizes. Now, here's a really interesting curve. This is an analysis. We don't have to go into the details of what this means. For technical people, these are spherical harmonic multipoles, but don't worry about that. If you take this picture and analyze the size of the blobs of different temperatures, and you can build a mathematical description that looks like this. And the measurements taken from an early version of this picture are these black crosses. You see they go up and down and so forth. There is a model for what went on in the very earliest seconds or fractions of a second of the Big Bang called inflation. And if you take the inflation model invented by Alan Guth in 1980 and merge it with or introduce something called dark energy, you get this red curve, which matches the data very well. The thing I like about this drawing is it also includes theories that didn't work. There's a theory called the open universe, which says the universe has a hyperbolic shape, or sorry, spherical shape and so forth. This green one has inflation, Guth's model for the very earliest time, without dark energy. That doesn't work. Cosmic strings, that doesn't work. But inflation and dark energy work. And so this curve and the refinements of it from better measurements, which are included right here, look how, this is from a mission that ended in 2015. Look how the data match the theory. I mean, it's right on. And this theory tells us the density of atoms of the type we're made of in the universe and it comes in at 4%. So here's what we currently understand about the makeup of the current universe, that we are made of this stuff. 4 to 5% of the universe is atoms of the type we rely on for the construct, and this includes all the stars, all the galaxies, all the humans, basketballs, tacos, everything that we're familiar with is in this slice. We know from independent measurements that there's something called dark matter, which is impacting the way galaxies form and evolve, 24%. And we now know from measurement of the expansion of the universe that most of the universe is made up of something called dark energy. We don't know anything about it. We don't know what it's made of, but it is propelling the expansion and the acceleration of the expansion of the universe. But what I want you to take away from this is, from the cosmic microwave background analysis, we get that 4.6% of the universe is atoms of our type. From Big Bang nucleosynthesis, we get the same number. We get 4 to 5% of the universe is made up of atoms. That's why I said when we first started this evening that we have independent measurements that complement one another, and they focus on some key numbers. And this captures those key numbers. And this provides us, now we know enough to explain virtually all of chemistry. So this is a very nice version of the periodic table. Anything that has this blue color was created in the Big Bang. The rest of the colors depict how those elements were formed. So hydrogen, almost entirely made in the Big Bang. Lithium, see, has a little component of Big Bang, and it has some cosmic ray fission producing it, and dying stars produce this. This is what's making the lithium problem that I mentioned so difficult, because modern stars are making lithium. So when you go out looking for lithium and try to understand what happened in the early universe, you have to somehow accurately subtract what's the result of current activity. Exploding massive stars give us sodium and magnesium and so forth. And merging neutron stars, we get these heavy elements. Merging neutron stars. And we now have a new tool for studying merging neutron stars, gravitational wave sensor. We have 2 of them online, one pair in the United States, one in Italy, and one coming online late this year in Japan. So this is the new version of the periodic table we all studied in high school chemistry, but we now know where all this stuff came from. So we're almost out of time. I want to leave some time for questions. This is more detail on the subatomic world. And I do want to mention one thing, and that has to do with neutrons. I already mentioned, and here it's depicted, that neutrons are not stable. Neutrons, left to their own devices, after about 10 or 15 minutes, decay into a proton, electron, and this neutrino thing. But there's a problem with it. Oh yeah, and this is a joke. See, it's really simple what's going on here. You have all these pieces flying around and interacting. It's not simple. If you're interested in this, I like this book. It's called We Have No Idea. And it's kind of fun. It has a lot of cartoons, but it has serious modern science in it. Be wary of older books. And by older, I mean if something is more than, say, 15 years old, it's the science that was understood at the time is probably obsolete. But this is a fun little book. And if you have a junior high or high school student that's interested in these things, get them this book because it's easy to read, has little cartoons explaining these things. This is more detail on the subatomic particle zoo, but here's the mystery. Here's a neutron, and we now describe neutrons as being made up of 3 particles. They're called quarks. They have these odd names. So we have an up quark and 2 downs. If you mix those things together, you get a neutron. And this theory is extremely successful. It predicts all kinds of things seen in the subatomic world where collisions are simulated, not simulated, they actually collide things and measure all these subatomic particles. So we have a neutron made up this way, up and two downs. A proton is two ups and a down. And then as this thing decays, it, as I've shown before, it produces a proton, an electron, and a neutrino. Here's the mystery. In the laboratory, an isolated neutron will sit, you can do this, you can build them and put them in a little, literally in a bottle, and they last about 15 minutes. And all that's happened when that neutron becomes a proton and this other stuff is this down quark becomes an up quark. As soon as that happens, it's like the Seattle player changing jerseys, and now he's playing for Tampa Bay. So all that's happened here is a neutron decays to a proton. There are two mysteries about this. Protons, once they form, as far as we can tell, they're completely stable. They have a lifetime longer than the age of the universe. We don't know why a this configuration is stable in an atom, or if you can take a proton and isolate it, it's stable. We don't understand why neutrons are unstable and protons are stable. Moreover, we don't understand why neutrons in an atom, which is how we build more heavier elements, why are the neutrons in the nucleus of an atom stable? If you have an atom of iron and you just leave it on the table, we never observe that mutating into another element. Now, if you jam a few extra neutrons into iron, you can make it a radioactive isotope. That's not what we're talking about. I'm saying we never observe a neutron in a stable iron atom suddenly become a proton and you get a new chemical element. That doesn't happen. Nobody knows why. And what's even weirder is if you take neutrons, instead of storing them in a bottle where they last for 15 minutes, roughly, if you put them in a beam and you shoot the beam of neutrons through your lab and you measure the decay rate there, you don't get the same result. This is on the cutting edge of physics research right now. There's a difference of about 9 seconds between a beam of neutron, the lifetime or the half-life of neutrons in a beam is different than by 1% from when you put them in a bottle. Nobody knows why that's happening. There's more detail here on the inflationary universe. We're not going to go into that because we're out of time. But right now, the best evidence we have about how the universe started is captured. Let me go back to the key drawing. I apologize, don't get dizzy because I'm doing this. Right there. We have a variety of different techniques for studying the universe and the density of atoms of the type we're made of, and they all point to this number. This is a complete mystery. Dark energy, nobody knows what it is, but we see its effects. And dark matter, also a mystery. So right now, we understand 5% of the universe. Okay? That's my presentation.
Wow, that was great.
Thank you.
And possibly, could the end of this talk be another talk?
Well, yeah, there's much more to this. We kind of hurried at the end because I included too many topics, but there's probably 4 or 5 other. Let me scroll in the background here and look at. Yeah, there's probably 4 other lectures that we can spread out over a period of time. The inflationary universe is particularly interesting. Guth, here's a poor Alan Guth, who invented the inflationary universe, probably can't win a Nobel Prize because they concentrate on awarding prizes to people who had a theory that's confirmed by measurement. And we have no way, as yet, we have no practical way to measure what went on in the inflationary period, which occurred way back, right, 10 to the minus 25th seconds after the bang happened. So Guth is he's still highly successful. He's credited with explaining 3 dilemmas that were unexplained until he brought forth his theory. I didn't have the time to talk about them tonight, but he's a highly revered character. I walked past his office once when I was visiting MIT. So I thought I saw somebody who was about to ask a question.
I've got a question, if I may.
Sure.
So what we know is the origin of the universe as far as the 4% of the matter that we relate to. But that doesn't mean the dark matter and the dark energy could not have preceded that Big Bang, does it?
Yeah, I know. So interesting question, because you may have noticed in the news just a week and a half ago, Nobel Prize in Physics was awarded for this year to 3 people, Andrea Ghez, who is an astronomer at UCLA, and her colleague who measured the motion of stars deep in our galaxy, and Roger Penrose. Roger Penrose is a theoretical, he's a mathematician who applied his math techniques to understanding black holes. And he's been in the news since he was awarded a share of the Nobel Prize because he has presented his theory that massive black holes in our current universe are leftovers from prior universes that existed before the bang that led to the current universe we live in. And so when we think about inheritance, and his ideas are controversial, but by golly, he just won a Nobel Prize, so he has to be taken seriously. If you think about inheritance from older universes to our current universe, dark energy and dark matter could be included in that bequest that we are enjoying now. And by the way, just make it clear, the emergence of dark energy as a dominating force in our universe was first seen by Einstein, and he was offended by this idea. He thought he was dealing with a static universe. This is back in the 1920s. And he set aside the idea of an expanding universe by neutralizing the idea of dark energy. And it stayed dead until people actually observed very, very ancient galaxies going away from us and accelerating the rate at which they are disappearing. And that led to a Nobel Prize, 1997, I think.
98, yeah.
Yeah, 98. Yes, so other questions?
Yes, I have a question.
Sure.
You started with this was excellent, thank you. I've given talks on this topic, but on a much simpler line. You gave me some great detail, but it would be really super if you progressed from the start of the universe and finished with a talk about how it's going to end. I was challenged to give a talk about that. It was the most terrifying talk I ever gave, but it's fascinating to, all the different theories that how the universe will end, whether it's going to just expand, it's going to collapse. There are many theories. And I thought that would be a super one that you would give because you're so knowledgeable about the whole process.
Well, thank you. And let me make a couple of comments.
Mm-hmm.
The understanding we have now of the geometry of the universe says that our universe has a flat geometry. And by that we mean everything we see, it makes it look like, can you see a piece of paper? I know I have my background turned on, but I'm holding up the piece of paper, that it's flat. That's the geometry we get from our measurements.
Right.
But let me point out something. I'm building something for you to look at. This is also flat. This is the shape. This could be the shape of the universe because I built it out of a geometrically flat surface. I did not have to crease the surface to create this tube. And it's important. And when I lecture on this topic with my other students, let me turn off the.
Can't hear you now.
You're muted.
You're muted.
You muted it.
When you turn it off, you muted it.
Unmute.
Turn off mute.
Ed.
Oh, sorry. Didn't know it was muted. So the idea is this is a flat geometry, but not a flat shape. And this is a topic of a lot of research right now. What is the shape of the universe? Could be something like this. Did you hear me talk about triangles? No. Okay. So what I was saying is if I drew a triangle on this before I roll it up, that triangle will have 3 included angles totaling 180 degrees. If I draw 2 parallel lines before I roll it up, they will stay parallel, forever. Then if I roll it up, no, that doesn't change. The triangle still has, you'll still have 3 angles that total to 180. That, I'm trying to depict the difference between the geometry and the shape. Right now, we believe the universe is flat and will continue expanding forever. So, but anyway, Judy, thanks for the comments. And that's a good topic for a future talk.
I mean, we should get that at the end. I'd like you to progress with where you started.
Yeah. Well, I tried to cover a lot of things. So there was
That's okay.
I have a question for you.
Yes, sir.
When you were talking about this beam of neutrinos and not getting the same value.
No,
how fast?
No, I have to interrupt. A beam of neutrons, not neutrinos.
Neutrons, I meant.
Yes,
sorry. All right. How fast are they moving? And is there any relativistic explanation for the difference in observation?
No, they're slow neutrons.
Right.
They're slow neutrons produced by, you could buy a little radioactive source and put it in a protective lead container and drill a little hole in that container and you get a beam of neutrons coming out. And people are just scratching their heads why we can't get agreement between bottle and beam neutrons. It's a strange thing.
Okay, thank you.
Harold, looks like Harold.
Yeah, Ed, that was fascinating.
Great. Thank you.
We have to get one question in here by Henry.
Oh yeah, because Henry probably has to go to bed soon.
Why don't you go first, Henry?
Go ahead, Henry.
All right, Henry.
Get close.
Question.
Do you remember what it was? Did you forget? I think you forgot.
No, I didn't.
I'm gonna explain it.
Well.
What's that? Let me take another one.
But isn't there more stuff? I saw more slides that explain stuff.
Yes, Henry, there are many more slides in this presentation. In fact, it's part of a, let me think for a second, a 16-hour series of lectures that I use to talk to adult students through the University of Denver. And I will be doing that starting in January. So if you're interested in seeing the entire 16 hours on modern cosmology is what the class is called, you can, because of the virus, we're all familiar with logging on and doing what we're doing tonight. Those of you who are interested in seeing the whole thing, doesn't matter where you are, you can sign up with the University of Denver, and I will be talking about this in more detail, a 16-hour lecture series. So yes, there are many more, and Henry's in the background doing this. He wants to attend. With your schoolwork, but
you can always practice on Science for the Board.
That's right. So thanks for that question. Okay, what happened to Harold? Harold, you had a question.
Go ahead. Yeah, the first that was fascinating.
Good, thank you.
One and other interesting paradox, and I'm wondering if you know more about this recently than I do. I mean, there are two ways to measure the Hubble constant, one out of the early universe and one by direct measurement of the rate of expansion.
Right.
People here, right, the Hubble constant gives you a rate at which the universe is expanding. And at one point you had these two different measurements, but enough uncertainty that you could say, well, this is the number 70 is consistent with both of them. And right. Now we're close to what, a 4.5 sigma difference.
Yeah, it's a huge, huge problem. So yes, if you want me to talk about that, I can for a minute or two. Or did you have something more you wanted to say?
No, well, the other thing was just to sort of mention I mentioned this to Bruce earlier, that I was going to give a talk later on intelligent life in the universe and theories about that.
Okay.
Much
good.
later. But yeah, just interested in your thoughts on this, because I mean, it's an interesting paradox. And oh, by the way, let me mention one other thing for women in science, that Vera Rubin at Vassar essentially discovered the existence of dark matter,
right?
By looking at the matter to explain how our galaxy, well, I'll say this very loosely, but how objects in our galaxy are moving around the galactic center. There wasn't enough observable matter to explain it.
Right.
And, had she been somewhat later, I think she would have gotten the gold medal too.
Yeah.
I want to interject. You know, my alma mater, Mount Wilson and Palomar, it goes way back to some of the guys there. They looked at the galaxies and they didn't see enough stars to do the math. So this goes way, way back, this idea of dark matter. And it was actually infrared observation that really showed that there wasn't enough matter in these galaxies for them to do what they're doing in gravitational.
Yeah, so that what John says is true. Let me show real quick, a comment was just made that, so if we draw this is a curve, say, from 1970 to 2020. You should be seeing a whiteboard, are you?
Yeah, we see it.
Okay, so there was a scatter of measurements using different techniques. There's one technique, supernova observations.
Yep.
And we're talking now about measuring or the current value of the Hubble constant. When I do this, a lot of times I do this. Because the Hubble constant, which measures the rate at which distant objects are going away from us, it's not a constant. In the life of the universe, it's changed dramatically. But the current value is called the Hubble constant. And 1 over the Hubble constant is the age of the universe. So it matters. If you don't have the Hubble constant right, you don't know how old the universe is, which is important. So back in the day, in the 1970s, people started looking at different kinds of supernova events, usually a supernova type 2. And we have the cosmic microwave background data. And it was just a range of values centered on about 70 in some strange units. As time has progressed, both of these measurement techniques have gotten better and better. So by, say, 2000, we began to see the best measurement from supernova had of that value and an error bar. And the one from CMB had that value with an error bar. And everybody said, well, it's just lost in the air. Now the errors, the systematic errors are tiny. And we can see, no, they don't agree at all. There's a gigantic difference. The lower one is, Bruce will help me if I'm, or some, yeah, Bruce will help me. 68 and 73.
Yeah, I think so.
This is a stupendous problem that nobody can solve. We don't know what to do.
By the way, let me make a remark for people teaching astronomy. They always give these elaborate, calculations to relate the Hubble constant to the age of the universe. And what you do is you get the speed of light in there, and then you recognize the speed of light as 1 light year per year, and it pops out in a couple of lines.
Right.
Write everything with those units, and everything comes out very beautifully. Distance in light years and speeds, fractions of the speed of light, 1 light year per year.
Okay, so that's an interesting unsolved problem. So I want to make sure any young people who are still around, including Peter's daughter, just be aware there's plenty of work to do. So if you want to go into what's called astrophysics, do the right stuff, and you can help solve these problems. Okay, Peter, looks like Peter had a question.
Yeah, and John answered this in the chat to me, but it was kind of too short for me to get. So how come neutrons in nuclei don't decay within 15 minutes? What keeps them around longer?
Don't know. Why are neutrons stable in a nucleus? And if you isolate them, take them out of a reactor or something, they're unstable. Nobody knows.
Oh, yeah, Peter, I misunderstood your question. I thought you were talking about free neutrons flowing around, and that becomes relativistic. But yeah, I agree with that. Once you're in I didn't understand your question. Once they're in a nucleus, I don't know why they.
Right. And it's good that they don't decay in a nucleus, otherwise there wouldn't be atoms and there would be no hamburgers.
But isn't that
we would not be here.
Definition of strong force?
Sir?
Isn't that the definition of strong force?
No.
No.
It's related to the weak force, which moderates decay of a variety of things. So you don't know.
Cool. Okay.
You measure the mass of a neutron which is inside an atom in some way, and thus deduce.
Yeah, sort of. You can measure the mass of a nucleus very well.
Yeah.
And then you can infer the masses of the components because a neutron and proton don't have the same mass. However, there's other energy in there, namely the binding energy, which is related to the strong force.
Yeah, so you can't expect that. I'm just wondering, whether you get just something subtle. It wouldn't take much to perhaps overcome this force in terms of overcome the decay in terms of interactions.
Yeah, this is John. You know what, Peter? I'm going back to what I originally told you that, yeah, neutrons decay in about 12 minutes when they're free flying. And they can go much longer if you're going relativistic because time dilates. But when they're in a neutron,
no, in a nucleus,
it's totally different. I think it's totally different.
Yeah, the environment somehow protects the neutrons from decay, and that's a good thing.
So we probably should recognize that there is a lot more to say about this, and we don't want to do it all tonight. Now, right. Science for the Board is not going away, but we're going to take a hiatus until after the election. And I've been cranking out these, trying to get people to do these things for 6 months now, and I'm going to take a little break. And the people that I have a number of people here who have hinted that they might be willing to do another talk. Harold Hastings, Mr. Friedman, Scott Diamond, John Miller, Mr. Corbett, and Judy may have another talk up her sleeves. And Wells Cunningham, who has a PhD in physics and has a business making adhesives. I'd love to hear a lecture on adhesives.
Me too.
Yeah.
Me too. So Wells.
Me too. I just bought a book called Sticking Together about adhesives. I would love that too.
Unfortunately, I'm still trying too hard to make money making adhesives, put time into making a talk about adhesives, but I would love to.
That sounds great. I have to tell you a little personal history about this. I was introduced to the internet in 1993. The first contact I had with the internet was to pose a question about how does Scotch tape work? And I got mumbo. I knew, there's 4 forces in nature. There's gravity. I was pretty sure that's not gravity. There's the strong and weak nuclear forces. I was pretty sure it wasn't those. So it's an electromagnetic thing. But I got such mumbo jumbo. That was my immediate introduction to the idea is you can trust about 3% of what you find.
No. Actually, I'm a PhD in organic chemistry, so.
Einstein came to regret when he denied that there was dark matter and dark energy. He regretted that later. And the constant that he developed turns out to be a good constant to be used. That's not something that got thrown out from what he did.
Actually, he denied the expansion of the universe. He died well before dark matter and dark energy. And for the adhesive person, let me just say, I know it's some work. You can develop a presentation for this, but you hold on to it because you can use it later as well and add to it. And we'd love to hear about adhesives.
Actually, to be honest, that's exactly what I'm trying to do. I'm trying to make it into a sales call.
So, we could be a dry run. We could be a dry run for you.
Yeah, I thought this would be a good sales audience. It'll be a couple months, but yep, Bruce is correct.
Yeah, so you don't have to talk about everything. Just talk about something. I mean, that's the thing.
You're right.
Can I say how much I enjoyed your talk? And mention off to one side that I think we were both students at Maryland in about the same time in the 60s. I was a graduate student, you were an undergraduate, but in the 60s, we're both there. Maybe we met, I don't know.
in physics?
You finished in 66?
Yes, sir.
I finished in 69, but I was a grad student, so I didn't run across you. I don't recall.
I'll be darned. Who was your advisor?
Oh, Brad Kehoe was my advisor.
Oh, yeah.
High energy physics. And George Snow, those guys. Who were you with?
Go Terps. That's all. Go Terps. That's the.
Yeah, go Terps. Anyway, the talk, it was great. And more talks like this would also be great. Of course, I'm prejudiced. I love these things. I'm very embarrassed that I can't tell you why a bound neutron won't decay. I should know that. I'll look it up.
Yeah, look it up. It'll be good if somebody.
You could do a talk on it, Neil.
I could, but I'm embarrassed to give a talk if I don't know the answers to that.
Well, it looks like we have about.
That was a very insightful question. What is it about neutron decay? We don't know.
Who's talking?
Could you put that last periodic table back up for a moment, please? I want to get a screenshot of it.
Yeah, let me get a good picture. It's this. Now I'm going to do a share of the screen. So are you ready? Is that, well, actually, let me go into presentation mode. So bear with me for a second. It's drawing. This is easy to find if you just put a periodic table into Google and then go to the image, that it has a little show images.
But that's new.
I apologize. I did not put the reference for this. I like to normally do that. But yeah, this is the new way to think about.
I got it.
Good.
They have neptunium and plutonium shown here.
Yeah.
Neutron stars, but I thought that they were essentially, we had never detected them on Earth otherwise.
They are.
Are they just super low concentration?
Yes. Yeah. Uh-huh.
Whoa. Are we talking neutrinos or neutrons?
No. He's talking about neptunium 93 and plutonium 94. Plutonium's half-life is 16,000 years. So, or I think 16 or 64,000 years. So you have to have a source, a radio event to produce
synthesis.
Because whatever was on Earth when Earth was formed, of course, would have by now faded.
Yeah, it's like technetium used in medical imaging, which has
right. Okay, well, this has been, you guys have been a great audience, and that's what I'm looking for. But keep me in mind about University of Denver. And here's what I do. I publish, when I do my lectures, I record them as videos and post them on my YouTube page.
Great.
What is your YouTube?
I will show it to you. And
if you send all that stuff to me, Ed, I can forward it to the
okay, great.
to the list. If you don't
great.
Get it tonight.
That's
definitely. Because we have to go and it's 11 p.m. where we are.
Yeah, I know. But we talk about it forever, right?
Yeah.
One more thing. There's been a lot of chat about neutrinos. Those of us at FLIR actually know a neutrino expert, Dr. Austin Richards in Santa Barbara. He worked, before he came to FLIR, he worked on the Neutrino Observatory in Antarctica. And I've asked him to come. I don't think he's ever visited us. I will ping him again to try to do a lecture on neutrinos.
Great.
Oh, that'd be great.
That would, yeah, I'd love to do it.
Jeez.
Excellent.
Okay, folks. Once again, thanks for your attention and the great questions. And
thank you.
Thank you.
Very good.
Yeah, for sure. Thank you so much.
Excellent.
Thank you.
Okay, bye.
Who's that there with you, Peter?
This is Alana.
Alana. Hi, Alana.
Very interested in chemistry.
Oh.
Yeah.
Well, Wells is the heartthrob of all the young female chemistry students. So.
That story. 4-year-olds and 9.
My grandson had to go to sleep, but he is a lover of physics and mathematics. He's very bright. So I will show him this and the replay part.
Okay.
He
is recording.
He hates missing these things, but it's much later here and he gets up for